SO3 minus 2, if that is a product, what is the other product? H3O plus. What happened? This species looks most like this one. What changed to its structure? Lost a hydrogen. By losing a hydrogen, it is then defined as an acid. If it's acting as an acid, what must the other one act as? A base. What do bases do? Accept a hydrogen. So if I added a hydrogen to H2O, what would I have? H3O plus. Does everybody agree with that answer? Somebody disagrees. Somebody else disagrees. So two people disagree with this. What did those two people say the product was? Everybody can answer this because it's up on the board. Probably. Yeah, that you should turn that in today. HSO3 turns into H2SO3. What changed to its formula? We added a hydrogen. If we add a hydrogen to it, what did it act as? A base. If it acts as a base, what does the other one have to act as? An acid, which means our product would become? If H2O acts as an acid and loses a hydrogen, what does it become? OH minus. Okay, which would mean H2O acts as an acid. OH minus on the product side is a base.
That's what I'm saying.
Okay, but you have to be careful in your referencing. H2O is acting as an acid in the bottom case.
Right.
Yes.
So yes, what it became.
The structure, OH minus. We'll talk about the definition in just a second. Okay. Which answer is correct? The top one or the bottom one? Both are correct. Okay. HSO3 minus is a special molecule that can act as both an acid and a base. So both definitions are technically correct. Okay. For the sake of this slide, I didn't want to go through, I didn't want to go through and have it act. Actually, I don't even remember what I had it act as. What did I have it act as? I had it act as an acid, okay, which is what everybody else went through and drew it out as well. Okay. As long as you define it, you then get to predict what those products are, with some exceptions. Can I define SO3 minus 2 as an acid?
No.
Why not? Doesn't have a hydrogen. Okay. So there are molecules that you can define as acting as either an acid or a base. To be an acid, what did it need to have? Hydrogen. To be a base, what does it need to have? That's a harder question. Hydroxide? Does HSO3 minus have hydroxide? No. Whoa, that was the wrong button. What does it have? Yes, it has oxygen. That doesn't necessarily mean it can act as a base. What happened when it acts as a base? What does it become? H2SO3. What changed to go from HSO3 minus to H2SO3? Gained a hydrogen. That's the only thing that changed. The formula is identical except there's a hydrogen attached to it. Does everybody agree with that statement? So that minus sign right there also shows up on H2SO3? So is the only thing that changed that it's accepting a hydrogen? No, its charge is also changing. What's happening to its charge? It becomes what? More positive or less negative. To act as a base, what do we need to have? What is something that is negatively charged? At the simplest level, what is something that is negatively charged? Electrons. To act as a base, what do we need? Extra electrons. Why do we need those extra electrons? What are they being shared with? What does the base have to do? Accept H plus. To accept a positive charge, what does it need to have? Negative. It has to have those electrons. Okay. So depending on what we're looking at, we may change our perspective within those definitions and help us narrow down and classify our compounds. If we looked at hydroxide, hydroxide's our standard base. Does hydroxide have electrons? Yeah, that's why it's acting as a base. It's not that it's hydroxide, it's that it has that negative charge. It has extra electrons. Okay? We go back just a little bit further, and this is what Alexander was getting at. We go back to that first question. We started with SO3 minus 2, and it acts as a base, which means it accepts a hydrogen and it becomes HSO3 minus. Okay. What can HSO3 minus do? We saw down below it can do a whole bunch of different things. Okay. But we also have information about what it can do already written into that equation. How did I make HSO3 minus? Added hydrogen to what? I mixed SO3 minus 2 plus H3O plus to make, there's my reaction arrow, HSO3 minus. What other information is stashed into this equation that we haven't seen yet? Have we seen things on the left-hand side of an equation? Yes. Have we seen things on the right-hand side of an equation? Have we seen an arrow going from left to right? Yes. What's left? What does that arrow going from right to left mean? That reaction can run in reverse. So not only am I running the reaction with my reactants on my left and my products on my right, but I can change my perspective on this, and I can say my reactants are on the right, going to form products on the left. Okay? That is a confusing topic, okay? But that's what's happening within it. And this gets back to what Alexander was suggesting earlier. For HSO3 minus to act as a reactant and go backwards to become SO3 minus 2, what did it act as? What happened to HSO3 minus to become SO3 minus 2? Okay. It lost a hydrogen. It would be defined as an acid. Well, if it's an acid, what is the H2O acting as? It would then be a base. Why does this become problematic? Well, if I've got this reaction, I say identify the acid. What is your one answer? There could be two. There's an ambiguity now in the question, or in our definition of those terms. So what we want to do is remove that ambiguity as best as possible. And we do that by introducing a new term. Okay? That new term happens to be conjugate. And it's always a bad analogy, but it's the only word I can come up with ever. Heard of conjugal visits? Okay. Usually there's some kind of interpersonal relationship there for our conjugal visits. When we're looking at our reactions, the same thing is happening. SO3 minus 2 and HSO3 minus are conjugates of each other. They are related to each other. Okay? H3O plus and H2O are related to each other. Okay? They are conjugates of each other. Okay? So we have this idea of conjugate pairs. How do we then apply that into our definition? When we're looking at bases and acids, they are most commonly and least ambiguously referred to as the species as a reactant, and our reactants are typically found the left-hand side of the equation. So when I ask for acid, I'm asking for, which is H3O plus in this specific example. When I ask for the base, I'm asking for SO3 minus 2. What if I want you to say H2O? What we'll do is still define it as a base, but we'll add the term conjugate. H2O is the conjugate base. HSO3 minus is the conjugate acid. This removes some of the ambiguity of just saying what's the acid. Okay. In the previous circumstance, if I asked for what's the acid, there were two possibilities. Now when I add that term, what's the acid? It is only H3O plus. There is no choice. If I ask for the conjugate acid, that now changes the question, and I will be looking to my product side. I'm going to be looking at the acid on the product side. Make sense? Okay. Since you're all listening really well, this would be the perfect time to pause the video. If we look at the second equation, we've got our acid, we've got our base. Once we've defined HSO3 minus acting as the acid, we know it loses a hydrogen, which then means our product structure needs to become SO3 minus 2, and the other one would become H3O plus. Okay? We can then go through and label those as our conjugate bases and conjugate acids. Okay? So our conjugate partners are the most similar things on opposite sides of the equation. So back to that double arrow. Okay? What it's referring to is a concept known as equilibrium. Okay? It's saying that our reactions are reversible. How many reactions are reversible?
Not many.
All of them. Every single one is reversible. Okay? If it wasn't, we wouldn't actually be alive. Okay? The issue with reversibility, as we refer to it as reversible, is ease of reversibility. When we're saying a reversible reaction, we're saying that reaction is easily reversible. Okay? That's not technically true. All reactions are reversible, some of them more easily than others. Okay? If it happens to be a reaction that is very easy to reverse, then should I be concerned about the reverse reaction?
No.
If it is very easy to reverse, I should be very concerned about it, because what happens as soon as I form products? It can reverse, because it's easy to reverse. So if I have a reaction that is highly reversible, I need to be concerned about it. Okay. What if it is not easy to reverse? Well, then do I need to worry about the reverse? If that doesn't happen, I don't have to worry about it. Okay. I have a lot more control. The reaction goes in one direction. Typically, when we think about chemistry in 130 and in 151, guess what we're looking at? Non-reversible reactions. Okay, why? It's a hell of a lot easier to work with. As soon as it becomes reversible, it makes our mathematics all sorts of problematic. Because when you run a reaction, you expect X products. If I put together a bicycle with 2 wheels and a frame, I expect 1 bike at the end of it. Okay? What does it mean if that reaction is reversible? As soon as I build it, some little elf comes in and takes the bike apart. If that can happen easily, do I need to be concerned about it? Well, if I get on the bicycle and it can easily have a little elf jump on and take it apart while I'm riding it, that's a bit of a problem. Right? Same thing. It might be really funny for the elves and everybody watching me ride a bicycle. Okay. That's the same idea that's happening within our equilibrium reactions. Okay? How challenging of a concept is this? Second semester general chemistry devotes probably 10 weeks of the semester. Okay? 10 weeks spent on equilibrium because it is a very challenging concept to deal with. You've got lots of calculations to manipulate, okay? But it's all boiling down to the same general concept, which is what we'll be looking at here in just a second. And it all comes back to one extra little principle, LeChatlier's principle. Our reactions are going to change their conditions, okay, change the concentrations of whatever they can, reactants and products, that we achieve the equilibrium. We achieve an even point. Okay, so what is that even point? We've got a couple real-world, potentially real-world examples that we could look at here. How many people have seen a seesaw before? Okay, it's becoming less and less common. Apparently they're so dangerous you're not allowed to have them on playgrounds anymore. Yeah.
How? It really goes like
What do you mean how? Like really? Are you really gonna question that? Let's draw out the example here. Here's your little kid. Here's your big kid.
there's a lot of variables here.
There's a little bit of danger there.
But a little bit of danger, lots of
And-
entertainment.
Admittedly, I think we should all have seesaws because I think they're awesome.
A little bit of crocodile.
And it works really well for establishing equilibrium. Okay. What is equilibrium? Equilibrium says I am balanced between the reactants and the products. So that if I built my seesaw, what I'm looking at is saying my reactants being that blue block, if I place that on there, if I place the red block on there, to be at equilibrium, I'm balanced. What size should my red block be?
Same size.
The exact same size, which I probably won't do well, but let's say that's close enough. That's not much better. It's close enough. It's wider and shorter. That's why it works. Okay? So we're now at equilibrium. It has been balanced. Okay? All of our chemistry reactions will try to obtain this balance. What LeChatlier is saying is that now that the reaction's at equilibrium, it's balanced, let's mess with it. Because that's what we do as humans, right? As soon as somebody's balanced and perfectly stable, we run up and tackle them, okay? Throw them to the ground, mess with them. Do the same thing to our chemical reaction. How would I do that to the chemical reaction?
Add more.
I will add more. I add a second block. Am I in equilibrium now? No, that seesaw is going to tilt, okay, and it'll tilt towards the product or towards the reactants. So what does the reaction do to account for that tweak?
It reacts the reactants.
It reacts the reactants. Remember, our chemicals can be either direction, either reactants or products. If I've now taken it out of equilibrium by making a bunch of extra reactants, what we'll end up doing is removing some of those reactants and turning them into products. And now what do I have? Equilibrium again. That's what we're looking at when we look at an equilibrium reaction. Okay. Did I have to add more reactants? What else could I have done?
Could have taken reactants away.
Let's not do that yet, but what did you say, Obed? Let's add more product. Now what happens? Am I in equilibrium?
No.
No, so what happens? The reverse reaction occurs, and I convert some of that product into reactant. And I re-achieve my equilibrium. Okay? So if I add products to my equilibrium reaction, what happens? I get the reverse reaction. If I add reactants, I get the forward reaction. I can produce more products. Okay? As Chandler was suggesting, is there something else we could have done? What if I remove reactants? Am I at equilibrium anymore? So what has to happen? I'm going to remove some product and make that into reactant. The total amounts never change. But what I end up doing is chipping away at some and shifting the reaction one direction or another. Just by removing reactants, I could likewise remove products. That's also going to cause a similar type of shift. Kind of make sense?
What if you add something that cannot be reacted?
What if I add something that is neither a reactant nor a product? Well, if I add something that's not a reactant, should it go on the left side of my reaction? If it's not a reactant, no. Should it show up as a product? Is it a product? No. So where does it go?
In the middle?
Right in the middle in our seesaw example, which means it has no effect on the reaction. We only get an effect if we're adding reactants or products. Yes, Megan?
Isn't there something about like a catalyst?
So catalysts are an interesting feature. Catalysts will also not affect the equilibrium. What will they do? They will speed the process of getting to the equilibrium. Okay? So they will change the rate at which our reaction occurs, but they don't change the balance of our reactants and products. Okay? What if we had two divided chambers? This is our next example that we potentially see. I'm going to put kind of a barrier at the bottom, so a temporary barrier there. And I'm going to fill the left-hand side up with reactants. So this is reactants and products. My reactants, we're going to say, are a liquid. This is our analogy. What happens now that I've put my reactants in? I now say, reactants, do your thing. Try and make products. Okay, to do so, they must move from the reactant side to the product side. What happens? What's that? The product side will slowly fill up. What happens to the reactant side? It goes down till eventually what happens? I achieve balance. I've achieved my equilibrium. Okay? Yes, slightly Zen-like. What happens if I now move to what LeChatlier was suggesting? Let's add more product. Okay, so before I add it, what I want to do is pause the reaction. I'll pause it by putting my barrier back up. Okay, so now the things can't shift around. And I add more product. And I now say, okay, products, you can magically do what you need to do. I'm going to remove the barrier. What happens? The liquid shifts across. The product layer drops. The reactant layer rises. In the exact same manner as the seesaw did. Okay? If we expand this to Megan's suggestion of a catalyst, catalyst just speeds the reaction. How could I speed this reaction along?
Increase the size of the opening.
Increase the size of the opening. Am I still going to achieve level?
Yes.
Yeah, I'm just going to get there a lot faster because I can allow more throughput between those two barriers. Kind of make sense? Okay. So within this analogy, both analogies for that matter, would we ever expect a lot of product and very little reactant? The way this looks like is we'd always end up with equal amounts of both. It turns out that's not true. What's the assumption you're making? You have a different question?
Yeah, kind of. It has to do with the divided chambers.
Okay.
What if one of the chambers is thinner than
That's exactly what we're getting to here. Okay. What is the assumption we're making when we're saying the reactant concentration must equal the product concentration? In the case of the two divided chambers, we're saying those chambers are
the same?
the exact same. What happens if I make one of those chambers really, 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 really thin? If we had liquid, when we reached equilibrium, what would our liquids look like? Would it be straight across?
No.
No. What does it look like?
It's really low on the reactant side and then possibly overflowing on the product.
Higher on the product side. In this analogy, what we're saying is not the volume, but the height of that. So we end up producing more product. Okay. by changing the size of those containers. How do we do that same analysis with the seesaw?
Move the equilibrium either way.
Our equilibrium is in reference to the fulcrum. What if I put the fulcrum over here? Would I be in equilibrium right now? What do I need to do to make it equilibrium?
Reduce the weight on one side.
Increase.
I could reduce the weight or
Reduce the
add more weight. Would I be at equilibrium plus or minus now? Eventually, okay. So in this case, this reaction that I've now demonstrated there, does that favor the products or the reactants?
Reactants.
Which one is there more of? I have a giant blue box and I have a tiny red box.
Reactants.
Favors the reactants. There's more reactants. How could I change my reaction? Or if I'm actually looking at this, if you're now students, do you want to go into lab and do an experiment that produces very little product? Why not?
Less to study.
Okay. You go home to cook dinner, and you spend 5 hours trying to make dinner, and you are able to cook 1 grain of rice. You might be a really bad cook, but that's not going to be a fun process. You spend all of that time to produce very small amounts of something. What's going to be a better result for you as a student? You go into lab and you produce. Somebody's definitely on a diet. We want to produce as much product as possible. So our fulcrum is going to be shifted significantly to the product side. Ideally, our fulcrum will be shifted so far to the product side that
we don't have any.
I am overflowing with rice in the cooking example. I'm overflowing with product.
It's like you start with 2 grades and get like 3,000.
Yes.
That's really cool.
Right? So it all, again, the amounts are going to come down to how much I started with. So it's not 2 grains of rice becoming 3,000. It's saying those 2 grains of uncooked pieces of rice became 2 grains of cooked rice. Okay. An edible version of it. Kind of makes sense? So our equilibrium is the balance between our reactants and products. LeChatlier comes through and says we can change certain aspects about our reaction to get our equilibrium or to get to that equilibrium. Okay. If I had a situation, this is a much more challenging question, where this was my reaction, the seesaw. That was the reaction I was working with. How could I maximize the amount of product? Because in this case, I'm only going to get a tiny little amount, equal amount that I started with.
Just add more
Add more what?
reactant.
I could constantly be adding reactant in. As I constantly add reactant in, what happens?
More product.
More product is produced. Okay. So if I'm looking at a reaction, I can add more of one reactant into a pool to cause more products to form. That's a simple way to adjust our experiment. How else could we do it? At the same time I'm adding reactants, I should... What else is going to cause products to form?
Add more product.
If I add product, what happens? The weight on the product side goes down, it starts to achieve equilibrium. What do I want to do?
Subtract.
Remove the product. As I'm constantly siphoning off product and adding reactant, the reactant is then constantly trying to replenish the product, both because of the added weight of the reactant and because I've removed product as I'm doing it. And yes, Michael, you're exactly right. It is confusing. Because what we're looking at here doesn't involve any of the numbers. This is just the thought process behind it. Okay? And it is exceptionally confusing. The instant we bring numbers into it, it adds a whole other layer of stuff. Okay? Which we aren't doing this semester, so don't panic. I heard an O over there. Okay? That is why it gets so much time in a full class. Okay? But what you're responsible for is acknowledging that that's what's happening. That's what this course is supposed to do. Okay? To be exposed to it. Okay? The next part of this is that we didn't talk anything really about rate. Okay? Well, Megan suggested something about rate, that if we had our two divided chambers, how could I speed the reaction to form products faster? Okay, adding a catalyst. What does the catalyst do to this chamber?
Increases the opening between.
It increases the opening so the liquid can transfer across faster to the product side. Okay? So adding a catalyst can help speed the reaction. What else could speed the reaction?
Temperature.
Temperature. If we provide more energy, we speed the reaction. Why is that the case?
Because heat causes atoms to move faster.
Atoms move faster. The faster they move,
More likely they
if you're trying to find a date, if we just put you in a closed room and just say move faster, you're going to get a date faster. Who are you dating? You're by yourself in a closed room.
Imagination.
You're not going to be able to find a date fairly quickly. But if we put you in there with one potential date person, eventually you could potentially pick up a date because you have no choice. What's going to increase the likelihood that you'll be able to get that date? To have a date, what do you need to... So we've talked a couple of things there.
Money.
So catalyst. We could bring in alcohol as a catalyst to reduce the emotional barriers between those two people so that they do what? And be PG, talk with each other. They start to interact. What if you never interact? What if you never interact? Are you going to get a date? No. So you have to have that initial interaction. We have to have the two reactants mix. What if one is a solid and never moves, and the other one is a gas?
And what?
What's that?
The gas is too crazy for me.
The gas may move around, but the other one's not moving. We have to wait for one particle to make it to the other particle. How can we increase the likelihood that both particles are going to interact? If they're both in the same phase, and ideally gases. Okay. So we want to minimize phase differentials. Okay. We also suggested another one. You're that single person in there, you only have one potential date. How can we increase the likelihood of you getting a date?
Give you money. More potential
You
dates.
potentially add a catalyst by adding more money so that you like our alcohol. What else could we do?
More potential dates.
More potential dates. Increase the amount of potential dates. You're going to increase the likelihood. When we're looking at chemical reactions, it's much the same way, though we end up adding extra terms to them. Concentration. Okay. Do we have enough potential date sites?
You have too many.
Okay. Nature of the reactant. Okay. The nature is the phase. Okay. If we're mixing a solid with a gas, well, they won't interact very well. But if we had two gases, we'll get a lot more interactions between them. Okay. Mechanism. How does the reaction proceed? Okay. If we think back to that Hitch video, was it the first guy that came up? And I don't even remember what the hit line was. I got lost. You look like my next girlfriend. Okay. Was that a good mechanism to getting the date? No, that was a horrible way. Well, in that one relationship, that was a horrible way to getting a date. Okay? So changing how the reaction occurs can change whether we get products faster or slower. Okay? Temperature. Okay? If we increase heat, what does that do? Particles move. The faster they move, the more likely they collide, the more likely we get a reaction. Take it a step further. If we increase the heat, what happens to our solids? They change phase. They turn into liquids or gases. We increase the likelihood of interaction again. Okay? And then catalyst. We can add a catalyst. Somebody that comes in and says, here, let me introduce you two together. There's our date connection.
Or like money.
Money could be a catalyst depending on the people involved. Okay? So what we're looking at within our rates are largely the exact same things that we would see within the whole dating process. Okay? Those factors change how we get to equilibrium, but they don't change the equilibrium itself. Okay? Questions about that? Okay. So what does that mean as far as acids? If we take a look at H2O, how many of you are concerned about H2O? Yeah, that was kind of a bad question. That was too vague. Let's back off of that one. How many are concerned that H2O is going to physically hurt them?
H2O to pressure washer.
H2O, not H2O also, H2O. Okay. When you got up this morning and stepped into the shower, you're like, I got to make sure I'm not too close in this for too long.
Yeah, you're
Yes,
What?
You're assuming a lot better than you were showering this morning.
I actually got a shower this morning. It was amazing.
Alright, you're assuming I should. It gets cold.
Okay, so let's still go with H2O. Relatively benign, not concerned about it. As far as the acid-base characteristics, what does H2O potentially act as? What does H2O have? Hydrogen, which means H2O can act as an acid with the hydrogen. If we rewrote the formula of H2O, what else do we have?
base.
We have that OH, which could be a base. So water could act as both an acid and a base.
Granted, very weak acid or base.
That comes to our next point. It is a very weak acid or base, which means the balance between our acids and bases is
Fair,
equal. The equilibrium I'm looking at, reactants and products, water is at a perfect equilibrium, perfect balance between them. HCl, can anybody tell me what HCl is? Hydrochloric acid. Is anybody concerned about hydrochloric acid?
Yes.
Yes. Why are you concerned about hydrochloric acid? It burns. Why does it burn?
Very cold.
Why is it reactive? What does it produce that is reactive?
Hydrogen ion and pure form.
H plus and Cl minus. Which part of those are we concerned about? Why H plus and not Cl minus? It's an interesting question.
Because
H plus ends up being reactive and the Cl minus isn't. Okay. If you're ever concerned about which one is which one's the dangerous one, which one's not, think about your sources of chloride. Chloride is found in, fair enough, pools, also salt. And if chloride was particularly dangerous, what would happen, potentially, hopefully not after your final exam?
you could add a bit too much salt.
What would be the issue after our final exam that's potentially not happening with respect to chloride? Hopefully your face doesn't melt. Why? Where's chloride found?
Salt.
In salt. And salt is found in your tears. Mind blown.
Oh, you're making it funny.
A funny with some context. If crying was that big of an issue that our face melted every time we cried, I'd probably be a lot uglier than I already am. Right? We'd be a lot more concerned. I'm not concerned about that. It's not chloride that's the issue. It's H plus. If H plus is what I'm concerned about, where is it? Is it a reactant or a product in that equation?
Reactant. Oh, wait, it's a product.
Do I have H plus here? I have H bound to Cl. Do I have H plus? No. Where do I have H plus? On the product side. Which of these equilibriums at the bottom best represents HCl?
Would it be the one on the right? Because
In one case, I'm favoring reactants. In one case, I'm favoring products. Which one favors the products? Okay. So if we put on the left one, we're saying we have a lot of product here, and we have very little product here. And that would be balanced.
No.
Why not?
Because then it would take much as it takes of the product, reactant to lift the product.
When we're balanced in this fashion, we need to put down a lot more force here because of the lever arm action. That's actually the inverse of where it's supposed to be. The one on the left says we have a lot of product and very little reactant. The one on the right says very little reactant and a lot of product. If HCl is such a dangerous acid, and H plus is the part that is dangerous, which of these is most likely to represent it? The one on the right, because the one on the right has a lot more product. What's the bottom formula? Acetic acid. Are you as concerned about acetic acid as you are about hydrochloric? Why not?
Because it's found in a lot of stuff.
I don't accept that. Yes, it's found in a lot of stuff, but so is hydrochloric acid. That's actually going into your pool. Why are we less concerned about acetic acid?
Not as potent.
It is not as potent. It is not as strong, meaning it produces very little products. The one on the left best represents our acetic acid. Okay? Kind of makes sense? What if we went through to try to quantify this? Let's see. Hopefully it's right there. And I know you don't want to quantify it, so we're just going to kind of spitball. Don't make spitballs. I'm just guessing that I didn't have to clarify it. It was really supposed to be a joke that no one laughed at. Everybody thought was serious. What's that? I appreciate that. Let's quantify it. So our equilibrium gets defined, of course, since we have a new word and there's too many letters in that word, we define a new symbol to represent it because that's what we do. It gets defined as this capital K. Capital K is referring to the equilibrium constant. Okay. To calculate the equilibrium constant, it is defined as the concentration of products divided by the concentration of reactants. Okay, and I know we're now doing sort of numbers. Let's back away from the numbers and try and define the value of K for the one on the left. What would I expect the value of K to be? So between red or blue, which one do we want to define as a smaller number?
Blue. Blue's smaller.
That shape is smaller than that shape.
I'm not sure what you're doing.
Okay. We're looking at the left side.
That number's going to be smaller than the one on the right side.
So let's define the red one as 1.
Okay.
That's our nice small number. Why not point something, 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 something?
Because we're making it simple.
We're making it simple. So we can pick whatever numbers we want. 1 makes sense. What should I make the blue be?
2.
Okay.
2.
So I've heard 2. I've heard 5. I would argue even easier.
3. 1.5.
10. So what is K for the left?
Well,
1 over 10. If we wanted to get into fancy decimals, we could go through and say 0.1. Define K for the right.
1.
So our smaller shape will again pick a smaller number. What will that small number be? Our bigger shape will specify as a larger number, and we'll specify it as 10. When we go through and look at our K, what does our K become? 10. Okay. So an equilibrium constant that is bigger favors what? More products or more reactants? More products. And that comes from the definition and looking at our shapes and sizes off of our charts.
Okay.
Bigger K, more products. Smaller K, less products. Will I ever get a negative K?
No.
Why not? I'll kind of accept that. To be a negative K, the products or the reactants must be
Negative?
Negative. Can we have a negative concentration?
No.
No. We'll never have negative K values. Even with anything you can think of, we will never have negative K values. No. Okay? That's what we're getting at with our acids. So we've got strong acids and weak acids. Our strong acids are the ones that produce lots of products, so lots of H+. Our weak acids are the ones that don't produce a lot, which gets us to the next fun part. Okay? Strong acids completely ionize in water. This means when we hit water, we immediately turn into H+ and whatever its conjugate base is. Excuse me. This could be defined as strong electrolytes, which we've got a slide on in a second, but you guys already know because you did the lab last week. Weak acids and bases ionize to varying extents. Okay? That means sometimes they form products, sometimes they don't. We get in this weird kind of balance between them. That exact definition is ultimately defined in Chem 152, and that is where we would quantify equilibrium constants. Okay? The big picture within this class is that we want you to walk out and be able to think about chemicals and say what's safe, what's not safe. Okay? Which of those two do you think you should be more concerned about? The strong acids. Okay, so when you walk out of this class, I want you to be able to look at a label and say, that is a strong acid, I want to be careful with it. So when you look at that label, can you predict that it completely ionizes in water? I don't think you can. That's going to be really hard. So how are you going to know it's a strong acid? Well, you can look up its equilibrium value, that K value. How many times have you seen a K value written out? Yeah, you probably have never heard it. Okay, so that doesn't work. So we need some way to identify this. Well, there's two ways that we'll quantify it, or we'll define it. Number one, we'll tell you what the strong acids and the strong bases are. The strong acids, there's officially 7 of them. Okay? Depending on your chemistry instructor, they would ask you to memorize those. Okay? If you see me again for organic chemistry, I do kind of expect you to have those memorized. Okay? In particular, sulfuric acid, sorry I had to get it out, and hydrochloric acid, and, well, really, nitric acid. Okay? That's it. Okay, so you would be required to know that those are strong acids. Why do I want you to know they're strong acids? Well, what happens when they hit water? They immediately dissociate into their ions. So when I write out H2SO4, when I look at H2SO4 or think about it, what I'm seeing is not H2SO4, but I'm seeing 2H plus and SO4 minus 2. I've now skipped a step as far as thought process because I've immediately moved into their reactivity. Why did I say 2H plus and not just H plus? There's 2 H's in H2SO4.
So do they lose their strength after water then?
No, we no longer have that species. They've made their strength into the acidity of the solution. Okay, so the solution is still strongly acidic. Yes, still very, very dangerous. Just depending on the amounts. Okay.
So we need water, we're not going to make it.
What about weak acids and bases? How did we define our polar covalent bond? It's good. Look it up. How did we define our polar covalent bond? It's our rule of thumb. We look at it and say, that's a polar covalent bond. We said electronegativity sucks. You should keep bringing up electronegativity. Okay, well, actually, since you did, let's just test you. What is the electronegativity of sulfur and carbon? Okay, so we can't use electronegativity as our definition. What's our definition? You got notes? I want to know it. Non-metal also applies to non-polar covalent, so that doesn't work. I want polar covalent. What are you suggesting, Emily? Carbon and hydrogen is non-polar covalent. I didn't ask for that. I wanted polar covalent.
Everything but an ionic and a non-polar covalent.
How did we define polar covalent? It was everything that wasn't ionic or polar covalent. That was our definition. It was everything else. Guess what our ionic acids and bases are? Everything else that isn't a strong acid or a strong base. That's our definition. Okay? Keeps things relatively simple. We only have to memorize a few things if you are being forced to memorize it. You're not being forced to memorize it for this class. Okay? Questions about that? Okay.
So why do you not like burn the pool?
So one of the things we addressed here was whether it was strong or weak. Okay? There are plenty of cases where you have encountered hydrochloric acid and not burned off, like a pool. Why are you not melting in a pool, even though there's hydrochloric acid there? It's the concentration. Everything is poisonous. It depends on the concentration. Right? When we're looking at hydrochloric acid, in a pool, it's in there just high enough concentration to kill the bacteria, but then have a relatively minimal effect on you. Relatively.
Turn your eyes red.
Yes. Because your eyes happen to be one of the most sensitive organs in your body. So yeah, you expose those to hydrochloric acid, they freak out a little bit.
So then, random question.
Huh?
Why does your hair turn green in the pool then? If you're blonde.
I think it's the dye in your hair. I don't think it's that you're blonde. I think it's
It's like natural blonde.
Yeah, when I was little, my hair turned bright green.
natural blonde turn change.
It happens, it's the dye effect.
Well, you can't like wash it for like 3 days and then it'll turn green. It's not just like that.
It tries to convert it to the.
I'll have to look at that. I'll have to look at that. I'm sure I can figure that out. Yeah. How else can we specify our safety? So one way we can reference our strong versus our weak, but as Natalie's just suggesting, there's another issue that comes with this. Just because we have hydrochloric acid present doesn't mean that's going to kill us or is dangerous. We have to be worried about the concentration. Okay? So we could go through and look at the concentration. So if we think about little Timmy here, hey, watch out for that 0.015 molar H+ solution. It'll burn you. Is Timmy going to remember pretty much any of that information?
If he was smart, he would.
If he's smart, well, if he's smart, he's still alive. If he wasn't smart, he's probably dead, okay, if that was a problem. So we want to come up with some way that we can quantify this information that brings in some information about concentration, but that doesn't kill us with new units like molarity and big fancy numbers. Okay? So how can we quantify the concentration of our acid? I guarantee you've heard of this one. pH. What is pH? We said the H was the dangerous part. Guess what pH is a measure of? The concentration of the hydrogen ion. That's what pH is referencing. But we had to build it in such a way that we could reference that number relatively quickly, which goes back to our 0.15 molar solution. How can we tie that into our pH? This involves a fancy calculation, okay, which we'll get to in just a second here. What it will do is scale our concentration values, at least within normal ranges, into low and high pHs. And a pH scale that goes from 0 to 14, where 0 is incredibly acidic and 14 is incredibly basic. And 7 is perfectly in the middle, so is equal concentration of acid and base is neutral. Okay? So we can then refer to Timmy and say, watch out for that 0 pH solution. Okay? We bring in a relatively small number, 0 to 14, and we just add a new term, pH, and we can just say, watch out, that's kind of what this number means. It's a relatively simple idea, and it works fairly well. How do we get the pH value? So we could take paper to quantify it off of an experimental value. To calculate it, pH is the negative log of the concentration of hydrogen ions. Okay? So there's all sorts of reasons why we should panic about that. Number one, it says negative. Negative numbers screw everybody up. And then log. And what is a log? Logarithm. What is a logarithm? It's a function in your calculator. That's not too bad. Okay? Unfortunately, I don't know a lot about logs. I just know how to use them, okay, which is really kind of bad because we have to use that in 152. And we can bring in other terms. Base of 10. Okay, what does that mean? Yeah, I couldn't tell you either. Okay? So we're adding in a negative sign, which is a very simple calculation to screw up. We're adding in a log, which very few people understand. And we're now adding in a concentration of hydrogen ion, which is in weird powers of 10. Okay? So we get all sorts of things that make the pH calculation itself potentially confusing, which is why, again, it's a relatively small part of the class. Okay? Sorry, questions on that? So a question for you, how would you calculate the pOH? You would bless my soul? That's how you calculate the pOH? It's already blessed. Or beyond repair. One of the above. How do I calculate the pOH? Take the negative log of? Exactly right. The concentration of the hydroxide. The P is our symbol for taking the negative log of whatever we're looking at. So what if I wanted the P mic? Yeah, why not? Take the negative log of mic. That's how you get the P mic. Click on P Diddy, right? Sorry, I should have led with that. Electrolytes. Electrolytes, I think, is our last slide, is anything that when we add it to water completely ionizes. Okay? In the process of forming those ions, they allow for the passage of electric current, which we saw in the lab. So we got a bunch of examples up here. Okay? Sodium chloride, what happens when we add that to water? Yeah, you just did this, yeah. How about H2SO4? That one you literally just did.
Yeah, I know this.
H2SO4 is strong acid, which completely ionizes when it hits water. So H2SO4 would be an example of a strong electrolyte. Sodium hydroxide is strong base, which would suggest strong electrolyte. What happens when we add sodium chloride to water? It completely ionizes into sodium ions and chloride ions. That's what happens when it dissolves. We have a strong electrolyte. How do we know it ionizes? Sodium chloride, when we add it to water, gets the AQ suffix. Where's that suffix coming from? Our solubility rules, and how do we know it's AQ? Solubility rule number 1, anything with a group 1 metal, like sodium, is soluble in water. Okay. Calcium carbonate, iron hydroxide, iron 3 hydroxide, and silver bromide. Why weak? Weaking. Weak electrolytes, you're right. So now we need to come up with an idea why. I heard an option of they're not strong. Okay. So I'll accept that for the iron hydroxide, because that wasn't one of the strong ones. So that's a weak base. But I don't accept that for the calcium carbonate and the silver bromide. What do we need to use? Our solubility rules. And when we look up the solubility rules, what do we find out phase is? They are insoluble, which means they don't dissolve, which means they don't ionize, which means they're not strong electrolytes. They are, because I kept talking over you, weak electrolytes. Last ones. These are particularly irritating. At least the middle ones. Well, actually, no. What does that one look like? Acetic acid. If it's an acid, what does that mean? We would expect it to ionize, right? But then why wouldn't I have put that up in the strong or weak electrolytes? It's not strong and ends up classifying as a non-electrolyte or a very weak electrolyte. How would we know that? Because it's not strong. It's not one of our defined strong acids, which then by definition means it can't be a strong electrolyte. It's either going to be weak or a non-electrolyte, I would probably classify it up in the weak. It's kind of a bad classification there. The other two, this puts us under non-electrolytes. How can we identify those as non-electrolytes? Are they salts? Our non-electrolytes are, we can work with your positive attitude and just make it negative, it's okay. Are not salts, so we're looking at we're looking at polar covalent or non-polar covalent bonds. If we've got those, we're looking at a non-electrolyte as a first cut. Our weak electrolytes should be salts or ionic compounds that are not soluble. Our strong electrolytes should be strong acids and bases or incredibly soluble species. Okay? And with that, we have finished Chem 130.